This is a full sky temperature map from the COBE satellite. Along with later data from WMAP and Planck, it provides our most precise measurement of the cosmic microwave background, confirming the standard cosmological model across nearly all angular scales. But that confirmation has a strict limit. At the absolute largest observable scales, specifically multipoles below an L value of 30, the data departs from the standard model's assumption of statistical isotropy. The first departure is a clear boundary cutoff. The angular power spectrum registers a distinct deficit of power below L of 30 compared to what standard models predict. The second is a persistent parity asymmetry. At these large scales, odd L multipoles contain quantifiably more power than even L multipoles, giving a parity ratio of approximately 0.81. The third is a highly specific structural alignment. The preferred axes of the quadrupole and octupole align to within 10 degrees of each other, an arrangement so statistically unlikely it is routinely called the axis of evil. In isolation, each anomaly registers as a modest 2 to 3 sigma deviation. Together, they form a correlated large-angle physical structure that statistical chance does not anticipate. Mode identity theory proposes that these features are not statistical noise. Instead, the cosmic microwave background is the resonant standing wave pattern of a physically bounded topological cavity. This represents the proposed cavity, a Möbius surface embedded in a closed, simply connected 3-manifold. It has a co-moving circumference, L, and a transverse width, W. Completing one lap around the longitudinal strip glues opposite ends together with a mandatory reflection. If the observable universe is confined within this specific geometry, the 3 large-scale anomalies follow as mathematically inevitable boundary constraints. To see how, we apply the formal wave mechanics of the cavity. We start by separating the standing waves into longitudinal and transverse components. The perturbation modes, the waves that form the CMB anisotropies, carry strict Dirichlet conditions. Their amplitudes must drop exactly to 0 at the transverse edges of the embedded Möbius surface. This equation defines eigenvalues for these standing waves. Notice the transverse eigenfunctions, bounded strictly between the physical width limits of the cavity. The finite width forces a mathematical minimum eigenvalue for the ground state mode. Larger co-moving wavelengths physically cannot fit inside the boundaries. We can translate this geometric wave number into an observable angular scale on the sky by using the known co-moving distance to the surface of last scattering, roughly 14.0 gigaparsecs. First, the geometry dictates the transverse width. With a co-moving circumference of 2.1 gigaparsecs, the width W is roughly 1.34. This gives us a minimum wave number, Kmin, of approximately 2.34 per gigaparsec. We multiply that minimum wave number by our distance to last scattering and subtract 1/2. This yields a hard cutoff at a multiple of approximately 32. The observed low L power deficit matches this derived cutoff. The power drops exactly where the wavelengths become too large to exist inside the topology. Next, we isolate the mandatory transverse reflection of the Möbius identification rule. Looking at this matrix of transverse modes, reflection forces an anti-periodic condition along the longitudinal axis for even-numbered modes. Hitting the boundary flips their sign. Projecting these eigenmodes outward onto the spherical CMB sky couples the transverse reflection directly to angular parity. The suppression of even transverse modes translates geometrically into the suppression of even spherical multipoles. This mechanism dictates a parity ratio of less than 1, matching the observed sign of the anomaly without requiring any new microphysics. This non-orientable boundary also possesses a normal vector, a literal twist axis defining the spatial orientation of the identification. Because the lowest L eigenmodes are bounded by the entire geometry of the domain, they naturally inherit this twist as a preferred structural axis in space. The 10-degree alignment between the quadrupole and octupole is the observational signature of this twist. The universe is revealing the geometry of its fundamental domain. While the topology mandates the axis, the exact alignment we measure depends on the observer's specific coordinate phi parallel on the strip. We define the topological midpoint as 0.25. By relating the 10-degree alignment angle to our spatial frame, we calculate a displacement from that midpoint, delta F, of approximately 0.056. This places the observer at position 0.306, the primary input for our interference formula tracking direct and wrapped signals. We plug this in with an attenuation factor of 0.150, the ratio of domain circumference to last scattering distance. The interference equation yields a predicted parity ratio of exactly 0.814. The same geometric coordinate required to explain the 10-degree alignment independently outputs the precise 0.81 parity magnitude measured by the Planck satellite. One displacement produces both observables. This table summarizes the framework. A single topological structure accounts for the boundary cutoff, negative parity sign, and preferred axis. Inverting the equation and using the observed parity ratio to solve for position returns a location within 2% of the alignment estimate. This framework also fully aligns with the Planck mission's failure to find repeating, matched circles in the CMB sky. Standard searches assume topology behaves like an optical mirror, repeating identical visual patches. Mode identity theory dictates that the Möbius identification constrains the bounded eigenmode spectrum itself. A null result for optical repetition is exactly what a resonant cavity produces. We are measuring a standing wave pattern, not looking through a kaleidoscope. A robust physical model requires strict falsifiability, and this geometry provides an immediate test. The non-orientable identification must produce a correlated parity asymmetry in the CMB's polarization data. The TE and EE spectra must show a parity ratio of less than 1, with the exact same sign as the temperature data. Upcoming observations from Lightbird, from the CMB S4 array, and from Euclid DR1 will definitively test these precise constraints. The alignment we called an axis of evil reveals itself as the axis of light, a geometric map documenting our beginning.